Am I
It's
supposed to put them back?
You're supposed to put it back, but it's okay because I think the stockroom worker was already cleaning up, so they probably put it back.
Yeah, I was with my dad and I was like, I forgot to put my key away.
Yeah, it's okay.
Okay, so now I just put it on the little.
Yeah, on the little board at the end of class. So yeah, you just grab them and then put them back at the end. But yeah, it's okay.
Okay, thank you.
They probably got it. warming up, so I'll let you work on these problems for a little bit. Just let me know if you need help with them. I'll kind of walk around, see how y'all are doing. Did you just add the class?
Yeah, I had it on Monday.
Okay, yeah, just go ahead and have a seat. We're just warming up and practicing some conversions, and then I can catch you up.
Okay.
All right, let's start going over these. And so let's start with this one. So converting 2.5 meters to millimeters. And so walk me through what you did. So what conversion factor did we pick? So 1,000 millimeters is in 1 meter. So that's excellent, right? Meters cancels. We're going to get millimeters on top. And so that's, do we get 2,500 millimeters with that? And just double check my math. Questions on this problem? Remember, ask questions. So let's try the next one. So this one was tricky. So what were people's thoughts in trying to do this one?
2 steps.
So 2 steps, so I like that. And so let's just do that together. So let's go centimeters to meters, so 100 centimeters in a meter. And then we have to go from meters to kilometers. So 1,000 meters in 1 kilometer. So does that look good to y'all? And so then that gives us, and we can plug this into the calculator, or it looks like 4.5 times 10 to the -5 kilometers. Let me fire up my calculator so you guys can leave my mental math. Did anyone do a 1-step conversion on this? Yeah, you did?
Yeah.
And so what did you find as your factor, or kind of walk us through?
Yeah, I did 1.5 centimeters times 1 kilometer over 100,000 centimeters.
So 100,000. Excellent. And so you could have gotten this, and I assume this is how you saw it. So you have centimeters is 10 to the -2, kilometer is 10 to the 3rd. So you can subtract those to find the difference, or sorry, subtract the exponents to find the difference. And so you get the 10 to the 5th factor, or 100,000. So excellent. And so again, right, if you don't understand the 1-step conversion, that's fine. Stick to the 2-step, right? That's a lot easier to follow. But if you see the 1-step, go for it. Excellent. Questions on this one? Sorry, I don't want to move too fast. So then let's try, so what do we get for this one, the 77 meters to decimeters? What was our conversion factor? What do we get for the answer?
So 2 steps would be
All right, we're looking at the next one. What about 1-step? What's the conversion factor again?
1 decimeter over 1 times 10 to the -1.
So 1 decimeter is 1 times 10 to the -1 meters. So that is fine. So you could use the negative exponents, or personally I use the positive one. And again, they mean the same thing. So 77 meters equals to 10. There's 10 decimeters in 1 meter. So again, equivalent. And we can plug it into the calculator so everyone is satisfied. So 77 divided by 1 times 10 to the -1 And so that gives us 770 for our answer. And then, of course, same thing on top, if we'd use the positive number conversion factor, still gives us 770 decimeters. Questions on this one?
Can you write out for the top formula, if you are working in the scientific notation? Like, what does that look like?
Oh, so then scientific notation, we could just write that as 7.7.
Or no, how would you, like, with the scientific notation in the, not the solution, but in the formula, or in the equation, how would you work with that? Like, would you, oh, I guess you
Yeah, or you could write,
multiply 1 decimeter by 10?
sorry, I guess I got lost over what your question is, because 1 times 10 to the negative 1, that's the same thing as writing, because we could write 1 decimeter is 0.1 meters, right? That's the same thing. I don't know if that was your question.
Well, because I got the 7.7, so
Well, you,
is that?
because you should have gotten 7.7 times 10 to the 2.
And then if you do all that, then it'll equal 770.
Yeah, because this is the same thing, right? So this is just a scientific notation, so just writing it in different
I get it,
form.
once you put it in the decimal form.
Okay, yeah. And so what about the last two? So how do we go from decimeters to millimeters?
So it'd be 37 decimeters multiplied by, if you did one step, would it be multiplied by 100 millimeters over 1 decimeter?
Yep.
Okay, and that's the 100 factor.
Yeah, so get everybody up to speed. So decimeters, right, is 10 to the negative 1. Millimeters is 10 to the negative 3rd. So there's our 100 factor between them for the one-step conversion. And then so multiply, so you get 3,700 millimeters, or 3.7 times 10 to the 3rd millimeters. And then you could do the two-step conversion as well. So I'll write that out. So 37 decimeters. So then going from decimeters to meters. So there's 10 decimeters in a meter. And then going from meters to millimeters. So there's 1,000 millimeters. And then you can see that factor of 100 again crop out. Questions on this problem? And then what about this last one? So centimeters to millimeters. So a couple of different things you could do with this one. What approaches did we take? What do we do? Any thoughts over here?
I did the hard way. I know it's much easier, but I'll do centimeters, meters.
Let's do it. So, right, she mentions that's a hard way. Sometimes it's easier just to go back to the base unit, right? So even though it seems kind of hard, I think it's like a little bit better in some ways, right? Especially if you're having trouble kind of making these new conversion factors. So let's do that. So let's do centimeters, right? And we know how to get to our base unit. So meters, so there's 100 centimeters in a meter. And then now we can go from meters to millimeters. So 1 meter is 1,000 millimeters. So that's one way to do it. And so math works out, so zeros cancel, so times 10, so 0.02, oops, millimeters, sorry. Other ways to get there. And so you could have done your one-step conversion. So centimeter, right, is 10 to the negative 2. Millimeter is 10 to the negative 3. So there's your factor of 10 difference. Or you may also realize, especially if you were in lab and maybe playing with those rulers, or maybe you know, right, that there's 10 millimeters in 1 centimeter. So you might know that, or again, you could have derived that from our exponents there.
And then how would you derive that from the exponents?
So right, we have 10 to the negative 2 and 10 to the negative third. So then if we divide them, so then let's just take negative 3 divided by this 10 to the negative 2. So that's negative 3 minus 2. So there's your 10 factor. And then just write always more tiny units in the big units. So that helps you figure out which way. And then I'll just write that one step conversion. So 10 millimeters on top, centimeter on bottom, and we get our answer again. All right, any other thoughts about conversion factors for now? So we'll keep practicing this, and then, so the thing is, conversion factors will keep coming up over and over again, especially like stoichiometry. We'll be using, dimensional analysis to go from grams to moles to grams, and so we'll be using these skills kind of over and over again, and also in your lab, which you've been doing the first 2 labs. A lot of conversion factors, right? All those quarts and making your conversion factor. All right, so now let's get into sig figs. Since we've kind of been dancing around significant figures, and then of course they've been cropping up in lab. And so hopefully lab is kind of giving you the sense of the importance of significant figures. And so significant figures, right, they go back to some sort of physical quantity. So it depends upon, right, the measured values that you determine in lab, so it depends upon the precision of our glassware and equipment. And so again, you've been in lab a little bit, so you've gotten a taste of that. So you have your balances, right? And that's why you want to write every single digit that the balance gives you. And certain balances, right, give you more digits and also cost more money to be more precise. And again, you were playing around with your rulers as well, and all the different tools, right? So you saw how your graduated cylinder is kind of more accurate for measuring versus like your Erlenmeyer, which has larger error values. And so that's kind of where our significant figures come from, is again, how precisely can we report our number based upon our glassware. And then we have to manipulate our number, of course, just like you were doing, like determining density or other calculations, area. And so, of course, we'll be practicing with that. But then I wanted to bring up these conversion factors. So we mentioned them on Monday, but this is just re-emphasizing that we do not include conversion factors in our significant figures. So you could just kind of maybe put that. So do not count conversion factors. And so we usually just say that they have an infinite number of significant figures, so it doesn't matter. And right, that makes sense. So we have our conversion factor of 1 inch is 2.54 centimeters. And of course, right, we don't want to go down to 1 sig fig. So we want to keep all our sig figs. So it depends upon, again, your measurement. And so now let's go into these rules, because first we have to determine, well, how many sig figs did we start off with? And so the first rule is pretty self-explanatory. So all non-zero values are significant. So that makes sense, right? So every digit that you see on the balance is significant. And so this number 536, that has 3 sig figs. And then this next one is also pretty self-explanatory. So this is called the captive zero rule. And all this means is if you have this zero trapped between other non-zero numbers, then that zero has to be significant. That makes sense. So this number 6,703, so that has, again, 4 sig figs, so maybe this is a balance, again, showing you that all those numbers are significant. And so now these next two are not significant. And so I'll kind of summarize them. But basically these next two rules that we're going to look at, that they show magnitude. And well, what do we mean? Sorry, I can't spell magnitude. And so the first example is it says placeholder zeros to the left of a non-zero digit are not significant. So if we're looking at this number, so 0.0043, it only has 2 sig figs. And that's because all these in front are just showing how tiny. So they don't represent accuracy, but magnitude. And so maybe you want to write that. So showing how small. Now, if we had put a 0 after it, so let's say we'd written 0.00430, now this one would be significant. So now that's 3 sig figs. And then so the next rule, so this is now showing how big. So it says trailing zeros to the right after non-zero digit are not significant. And so this is when you don't have a decimal place. And so looking at 7,000, so this is only 1 sig fig, and all these zeros are just showing how big. And this could also be, again, a scale, so maybe this is 7,000 pounds, and this is really inaccurate, and so, again, those zeros are not significant.
With the trailing zeros, for your example, the 0.00430, if you added another zero, would that be significant or would it not? Because it's another trailing.
Yeah, so 0.00430.
Yeah.
Yeah,
So
now.
Would it be 4, would there still be 3?
Yeah, now it'd be 4 sig figs, because now this is showing, yes, we measured that accurately.
Okay.
Yeah. And then what kind of gets, and we'll do some of these examples. So then let's look at, well, what happens if we do 7,000, but then put a period? Now that's significant. So now once you have that decimal there, it is showing that is accurate. So then this is weird because usually you don't have a 0 there. But if you were, that would show 4 sig figs. And then same thing, so you could do 7,000.0, and now that's 5. So 1, 2, 3, 4, 5. And then, so we'll look at this number, so 32,040. So, right, you have the captive 0, so that is significant. But then this last 0 at the end, since there's no decimal place, we're assuming that it's just showing how big. And then this last rule is basically now saying, well, if we add kind of what I call unnecessary zeros, so now they are significant. So looking at this example, so 50.0, so now we added that decimal point and then another 0 after, so it's showing, yes, we measured accurately to the 10th place. And then same thing with this 0.0600, so that these first zeros, right, are showing how small But then all these at the end, so those are significant. So then we have 3 sig figs. And so you got a good taste of this in lab. And so like y'all were doing, you have to figure out basically your smallest hash mark. So we're looking at our graduated cylinder, so it has markings every 0.1 milliliter, so every 10th place, and then you all guesstimated to one more after. And so in this case, right, we have 4.5, and then you have to guesstimate that last digit. They wrote 4.56. I probably would have picked 4.57, but again, that's where that uncertainty factor comes in on that last sig fig. All right, let's do a little practice. So take a minute or two to look at those examples, and then we'll run through them, how many sig figs. And so you can just show me fingers. So what do we get for number 1? There's 54,000. So I see 2s everywhere. Excellent. So, and then what about number 2? So I see a bunch of 3 fingers. Excellent. What about number 3? Oh, 3 again. So good job on that one. So you all recognize that this was significant. And then what about 4? So fast on those 2s there. And then what about this last one? So different answers. So this one was tricky. So this one is 2. And so this is actually not the best way to write it because of kind of the confusion. So right, we have a 10 with a decimal point there. So it's trying to show that just these 2 are significant. But then kind of if you run across this scenario, probably what you want to do is write it in scientific notation. So you want to write 1.0 times 10 to the 1, and then writing it like this clearly shows, right, that we have 2 sig figs. And so we can kind of practice. And sometimes scientific notation, again, might be better if you're trying to show sig figs and you got a lot of zeros. So now if we do 1 times 10 to the 1, well, that's clearly 1 sig fig. We can do 1.00 times 10 to the 1, so now we have 3 sig figs. So just kind of keep that in mind as another way to help.
On number 3, the reason why that last 0 is significant is because it's after the non-zero digits that are after the decimal.
Yeah, so basically it's what we call unnecessary, right? Because it's not showing how small, it's just showing accuracy then if it's kind of not necessary.
But, if we, for example, you can write 1 times 10 to the 1 for number 5, or would you?
Yeah.
You would not write that because there is a decimal with 10.
Well, so I was saying, right, this would actually be the best way to write it down here, 1.0 times 10 to the 1. So then there's not this weird kind of confusion. Because even though we should know that that's 2 sig figs, right, what if you're reading that in a textbook and then you're not sure, is that a decimal or is it like a period, right? So if, for clarity, it's better to write it in scientific notation. But again, you may come across this in a textbook or something anyway, so you want to know how many sig figs.
Only why would it be 1.0? Is it just moving the decimal point so that you can see? Or
Yeah, well, because if you write 1.0, because your scientific notation should still reflect the sig figs. So by adding this, right, now you're showing that there's 2 sig figs, right? Because you don't need, right, the 0 to show 10, you need it to show the sig figs. So, right, that's why writing it as just 1 times 10 to the 1, now we only have 1 sig fig. Yeah, sig figs are fun. And so now let's do the math with sig figs, which again you've started doing in your lab. And so this is kind of the quick summary, but then we'll go through them. And so I always like multiplication and division just because it's a little easier. And so this one, it just depends on the least precise measured value. So whichever number has the lowest number of sig figs, that's the number of sig figs that you report in your answer. And again, we'll do a sample in just a second. And then with addition and subtraction, it matters how many places it's reported after the decimal. So the value with the smallest decimal measurement determines your sig figs. And again, we'll do that. All right, so let's try these examples. And then this helps us see why sig figs are important. So we're looking at this first one. So 3.56 times 4 centimeters. So how many sig figs are in 3.56? So I see some 3. And then what about our 4? So just 1. And now let's walk through this together. And so we punch this into our calculator, 4 times 3.56. And so the calculator spits out 14.24, right, just like it said. But now we have to round to 1 sig fig. So this is where things get weird, or at least weird in my opinion. So this just tells me, right, well, we probably wanted to give that 4 more decimal places when we originally reported that. But now that we have moved on from lab, we have to go with 1 sig fig, and so that's why it's rounded to 10 centimeters. And so that gives us our 1 sig fig.
So would it be 4 sig figs?
No, because we can only report to the 1, right, because of the 4 centimeters. So this is our limiting factor. So then once we round it, right, because this answer is 4 sig figs, but then we can only have 1 because of this 4. Yeah, so that goes back to those rules, right? So it goes back to, it's basically saying, right, if we were in lab and we're trying to get our area, but then we used a really inaccurate ruler so that we just got 4 centimeters, right? Then our area measurement can only be known to 1 sig fig. But of course, right, if you were in lab today, you're probably thinking, well, they probably should have written 4.00 centimeters. And then you would have your 3 sig figs, and then you could round, right, to 14.2. So then I'll just kind of write this as an aside. So what would have been better? So now we could have 3 sig figs for each. So that means we have 3 sig figs in our answer. and 14.2 centimeters squared.
And either way would be correct if it was on like if you wrote it the two different ways.
Well, it depends on how many sig figs, right?
Yeah.
Because the difference is the number of sig figs in this one. So if you were given the 4 centimeters, you want to report to 10. And then if you had been given this problem where they both have 3 sig figs, now you can report to 3 sig figs. Yeah.
Does that mean that depending on how many sig figs we're multiplying by, that should be like how many sig figs you're interested in?
Yeah, exactly, but it's the least number. Yeah, so now let's look at this one. So again, same thing, so we're doing multiplication. And so we have 1, 2, 3, 4 sig figs in our first measurement. But now we only have 2 sig figs in our second, right? So now this is our limiting measurement. And that means our answer can only be to 2 sig figs. And so now let's just punch it into the calculator so we can know that this text is correct. And so yes, we get 10.25. And then this is actually where we get one of those weird scenarios, right? Because we need to round to 2 sig figs. And so that gives us 10. But then we need a good way to show that, yes, that 0 is significant. So that's why they have here, right, use the scientific notation to remove that ambiguity of just having that decimal point. So does that make sense for this example? 10 to the 1, yeah. So 1.0 times 10 to the 1 milliliters squared would be that answer. And then, so same thing applies with division. So we have, right, 3 sig figs up there, but only 1 with R9. So, right, not a good measurement for lab. And so we'll punch this in so we can see. So 95 divided by 9. So of course, the calculator spits out 5. And then we have to round to 5 for that 1 sig fig. And so that's, again, you know, where the sig figs are important. So just kind of comparing. So if you had done 45.0 centimeters divided by, right, 9.0 centimeters, then we could report to 5.0 centimeters, or even, right, 95 divided by 9.00. So then we would have 3 sig figs. So just depending on your accuracy of your 2 values. If we had been given like 9.00 instead, yeah, so just showing our different combinations. And then this last example, so if we kind of deconvolute it, so we have 12 inches in 1 foot, so that's a conversion factor. Then 2.54 centimeters in an inch, well, that's a conversion factor. 100 meters in, or sorry, 1 meter in 100 centimeters, so that's a conversion factor. So all these were conversion factors, right? So they don't matter in the sig figs. And then we had 2 sig figs to begin with. So then once we do all our math, calculator spits out this answer, and then we want to round to 1.4 to give us those 2 sig figs. And so now if we look at addition and subtraction, so I kind of like to write it in what I call elementary school style here, where they're stacked on top. But then we can clearly see how many places after the decimal we can report. And so let's look at this example. So we have 23.467 plus 313.21. And of course, this is our limiting factor here. So this only goes 2 after. So we can only report to 2 after the decimal place. And so let's follow along. So we would punch this into our calculator, just like they've done. And so we get 336.677, and then we have to round to 2 after, so then we round up to 336.68 inches. And so then same thing for this bottom one. So notice, right, our top number, we can report to 0 after the decimal or none after. So we can't report any numbers. And so now we do our subtraction again. So 457 minus 0.68. And then we get 456.32, but then we have to round to our nearest whole number. So that's how they got 456 centimeters. Any questions about the sig figs, kind of addition, subtraction?
So what's the importance of significant figures? Why are we talking about
Well, it matters for like your lab and stuff, but it just goes back to like how accurately, like again, that you can report something and like what that value means. And later on, so we probably won't do it like in this chemistry class, but you also would talk about like error propagation and like, you know, how much error you have based upon like the accuracy of things. Because that's all that this goes back to, right? And if we go back to the beginning of this, right, it depends upon what we did in lab, right, and how precisely we were able to measure. And so that's part of what keeping the sig figs kind of shows us, is like how accurate was it? And then once you get like your rounded result, that kind of tells you, you know, a little bit about the value as well. So yeah, and it doesn't, it might not make like a whole amount of sense right now because you're just kind of getting into it, but it would also be like significant for, like, let's say you're trying to figure out the concentration of something in like parts per million or parts per billion. Like those are really small and accurate measurements, right? So you have to make sure, well, is my equipment even precise enough to make those measurements? So that's kind of what you're getting at as well. All right, let's see. So let's finish up with our temperature scales. And so I assume most people are familiar with our odd Fahrenheit scale. And so 32 degrees is set as our freezing point, 212 as boiling. And then Celsius was set to kind of, I don't know, make more sense in some ways. And so they set 0 as freezing, and then 100 as water boiling. But does anybody know where the Kelvin scale comes from? Yeah. Exactly. So absolute 0. So I'll repeat in case you didn't hear. But it's where there's the complete absence of motion. And so kind of what we had said, if you remember, right, on Monday, so we mentioned, okay, we have a solid particle, right, and it can't move. But then I said, well, that's not quite true, right, because your electron's still moving around in your solid. But then absolute 0 would be what happens if that movement stops, right? So there's absolutely no electron movement, nothing is moving. So that is absolute 0. And so absolute 0 is just a theoretical point. So now I was going to, I wanted to pull up the internet article. Let's see what I can find. I should have thought of this earlier. So So let's check in on the research. So they're trying to get down there. Oh, this news article was not the one I was looking for. It's kind of interesting. Oh my gosh. Of course, now the problem with journalism is everything is paywalled. And so they do a lot of weird stuff. So sometimes they do like lasers to try to like cancel out the vibrational movement of the atoms, which is kind of crazy. Yeah, I don't know what's. That is so weird because it's not. It doesn't look like that on my screen. Yeah, I don't know what that is. Oops. Sorry, one more time. Oh yeah, it is being super strange. All right, I don't know what's. And so this one highlights Alto University. So they got a rhodium metal down to almost 0. So that's really, really close. And so that's kind of cool. So if you want to look into it, I would definitely suggest kind of Googling around and seeing where the research stands on that. So of course they're trying to get closer and closer to absolute 0. And so this is also why we use the Kelvin scale a lot in chemistry. So this will come up later with kind of our gas laws and any sort of thermodynamics, which again you'll get a little taste of in this class as we survey our chemistry topics. But the reason why we have Kelvin scale is, again, it goes back to what it's based off of, so that complete absence of motion. And so that's why you want to have your 0 point there, and then it continues being positive for thermodynamic relevance, so you get answers that make sense. And then if you notice, so this is kind of convenient about the Kelvin and Celsius scale, is even though they appear really different, they scale by the same amount. So what that means is that, right, there's a 100-degree difference between water boiling and water freezing with both Kelvin and Celsius. So, right, notice that Fahrenheit is not the same. So it's that weird scale, which we can look at. So now let's get into the math. And so I would just write this down, although probably on an exam I would give you the formula. Wow, this is being, sorry, I just realized the screen is like gone funky on you. That's a new error. Just try to like refresh the connection. Come on. Uh-oh, come back. I mean, it is almost time to end lecture. I was just trying to get through the temperature scales. Well, let's see what the computers think about this class. Oh, there we go. I don't know why it's messed up. That's really irritating. I apologize. I'll have to call, like, tech support. What is it doing? I don't know why it's making mirrored things. It's not helping. I'm just trying to like trick it. There we go. That kind of works. It shows up normally on my screen in my recording, so. Yeah, I've never seen this error before. That's a new one just for your class. And so you can write this down, but notice, of course, the conversion factors are a little odd for Fahrenheit to Celsius, and so most of the time I ignore Fahrenheit unless I'm talking about the weather. And yeah, I have absolutely no idea what the boiling points of substances are in Fahrenheit, and I absolutely can't describe to you the weather in Celsius. I know, not useful. And so just note order of operations for this Fahrenheit to Celsius conversion. So you have to do the subtraction first, and it's in parentheses, and then times 5/9. And so you might also see this in the decimal form. So times 555, and then 9/5 is 1.8. So you might see other forms of that using the decimals. And this is, I think, the nice, easy conversion. And so your Kelvin and Celsius scale differ by 273. And so you just add 273 to your temperature in Celsius to get your Kelvin. And I think in the homework / if you see more precise conversions, it's like 273.15. But really, so there's a little caveat in your homework because it uses this term. So what is the temperature, I think, in Kelvin of exactly 0 degrees Celsius? And so just because the homework uses that term exactly, it's looking for this number with the 0.15. At least that's kind of what it's getting at, the exact conversion. But in reality, your thermometers are probably not that precise. And so, right, you'll be in lab, you'll probably see, okay, well, my temperature in lab is about 20 degrees Celsius. And so we would just add 273, so that'd be 293 Kelvin. And we usually ignore that 0.15 since we don't measure our temperature that precisely. But it's just kind of there, so you know it's there, and that's where it crops up. I'm not going to be looking to trick you guys on an exam with this like exactly versus like 0 degrees, but that's the point that the homework was trying to make with that wording. But again, I'm not trying to trick y'all. And then let's do this last bit, even though my computer's misbehaving. I just wanted to finish chapter 1. And so this last bit is we have density. So density is just defined as our ratio of mass to volume. So we just divide density as mass over volume. And then have you guys seen this triangle trick? So some people yes, some people no. So if you haven't seen it, this is really good to help you with the math if you're trying to convert from one to the other or find one. And so the trick is you cover whatever variable you're trying to find. So let's just say we're trying to find the mass, and we were given density and volume. So then you cover mass up, and then density and volume are right next to each other, so you know to multiply. Same thing, so density, obviously, right, that goes back to your formula. So you're trying to solve for density. You just divide mass divided by volume. But then if you wanted to find volume, so cover volume, and then it gives you mass divided by density. And of course, you can also use your dimensional analysis. So we'll do that for this example problem. And so this one, so now practicing our density. So if we have 73.2 milliliters of liquid, has a mass of 61.5 grams, what's our density? And so notice your density units could change. So it's always going to be some sort of grams per volume, but right, it could be like kilograms per liter, maybe ounces per quart. So just kind of be aware of that. And then also know that 1 centimeter cubed is 1 milliliter. So that's also useful. So then density, we'll do this one. So divided by 73. And then, of course, 3 sig figs on both of those. And so we should get 0.80 for our density. And you want to include that 0 so that you have 3 sig figs. All right, try this last one. And so I'm just showing the dimensional analysis. And so again, right, you could use your triangle trick. So it says determine the volume if we have an object that has a mass of 455.6 and a density of 19.3. So then if we cover our variable volume, so then it's showing us, well, let's do mass divided by density. But then if we plug that in, right, double check that your dimensional analysis makes sense. So divided by our density. So that means 1 centimeter cubed on top, 19.3 grams on bottom. And then notice, right, those grams cancel out really nicely, leaving you with some centimeters cubed or milliliters on top, which is what you're looking for. And so did everybody get D for that one? See, lots of nods. So D, and then yes, right, they have 3 sig figs on all the answer, but we're just kind of sanity checking that's correct. So we have 3 sig figs there, so that limits us. So that's D. And then the last part of this is just a small definition that's in your book. And so your book is kind of interesting. So it mentions specific gravity, but your book defines it a little differently in that it's a density of a substance compared to the density of water. So normally the more broad definition for specific gravity is it could be compared to any substance. But then what's the density of water? You guys remember or know? So it's 1. So 1 gram per milliliter. So water is kind of like our standard. But then it's kind of silly to me to have the specific gravity of a substance, because then basically it just becomes unitless. And so I'll show you what I mean. And so, right, let's say the density of hexane. So hexane is just an organic substance. And so its density is 0.661 grams per milliliter. But then if you were to find the specific gravity, and then as your book defines it compared to water, then you just take this divided by 1, and then it just becomes unitless. So then you end up with 0.661 for your specific gravity. So it feels kind of silly, but it's in your book as your definition of what specific gravity is. So just know that it's a comparison of two densities. All right, so that concludes the lecture. And so we're kind of practicing our usual format, even though we don't really have like a heavy quiz. And so what I try to do is I only try to lecture for an hour. I did kind of go over 10 minutes trying to finish up the chapter. But then I try to give you a 10-minute break, and then we do our quiz of the week. But this week's quiz, like I said, is just a welcome assignment. So just, why are you taking this class? How can I help you? Type of thing. But then the rest of the time is yours. So like I said, normally you do your quiz, and then of course if you want to leave, you can leave. But otherwise, use that time to practice, ask questions, and just get additional help with things. All right, so I'll go ahead and pass out our quiz, aka welcome assignment. And then if you need to go to the bathroom or whatever, do that. I'm here for questions. If you want to rush the welcome assignment and leave, you can also do that as well.